All right, this is your video on uncertainty in measurement and significant figures. So let's go ahead and take a look at what measurements are. Okay, so I'm going to go ahead and draw a ruler, right? Obviously here I'm going to measure length, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. I don't care. So that's going over there. So, and this goes 1, this is 2, right? Now, if I was to have, say, some sort of object, and it was about that long, and I wanted to measure it, understand that if this is in centimeters, okay, that when I have this measurement of whatever this red thing is, okay, I need to be able to not only measure it by what's calibrated on my device, in this case the ruler, but I should also be able to estimate a value. Now the reason why we have an estimation is because for every single measurement you do, there's always going to be some level of uncertainty. Okay? So if I was to zoom in on this little particular piece right here, right, and I'm looking at that, I'm thinking, well, that's falling right about there, which isn't quite at that line of 1.4, right? So, important to note that when I have this uncertainty, right, because I have to estimate what that is. Okay, so if I want to know what this red line's length is in centimeters, I'm going to go, it's 1 centimeter, and this is 1.1, this is 1.2, this is 1.3, and that's 1.4. Okay, so this line is somewhere between 1.3 and 1.4 centimeters. Right, 1.3 centimeters, 1.4 centimeters. Well, because you could look at it from, who knows, maybe from your perspective on your computer screen or on your phone, you're looking at that and going, oh, that looks about a 1.35 or 1.39 or 1.36. Okay, so because there's that uncertainty of what that actual last digit is, okay, you need to make an estimate. Okay, it is not appropriate to just round. Oh, that's about 1.4. Flat out, it did not reach that 1.4 line, so you cannot say that it was 1.4 centimeters. So you have to give an estimation, right? I am going to go about 1.38. Okay, I'm saying that's 1.38 centimeters. Okay. Now, how accurate am I? Remember, accuracy is how close I am to the actual value. So if I was to really get the length from a more I guess a better refined tool, let's say I ended up with 1.39 centimeters as the actual value of the length of that object. Okay? Well, 1.38, 1.39, that was a pretty accurate number, okay? Or a pretty accurate measurement. Now, if I was just to round it up to 1.4, you're thinking, well, isn't that the same distance? Or is the same distance from what it really was? So isn't your error, comparable? And my answer is no, because when I look at this value right here of 1.38, that means that I made a measurement to the 10th place, and then I estimated the 100th place. Okay, because that's what this really means. If I was to have 1.4 like I have right here, what that means is I am able to get an estimate to the 1's place, which is the 1, and then I have to estimate the 10th place. Okay, so that estimation always has to be there if you are to get a decent and an applicable value for whatever measurement you're taking. Okay, now just to kind of review with our idea of accuracy and versus like precision, if I was to measure this red piece of thing 3 times and I ended up with 1.38, 1.37, and 1.38, okay, that would also be those would be precise measurements because they're all close to each other. Remember, accuracy is how close the measurement is to what it really, what the object's true value is. Okay, for example, 1.38 to 1.39, that's pretty accurate, right? If I was 1.45 or 1.72, right, that would not be an accurate value because it's farther away, or it's pretty far away from the actual value. And then precise is if I have multiple measurements, how close are they to each other? So 1.37, 1.38, 1.37 again, or 1.38 again, right? Those are all close together, so I would say it's precise. If I had 1.38 and then I had 1.72 and then I had 0.99, right? Those numbers are not near each other, so I would not call them precise. And honestly, as a group, they would not be considered accurate either. Okay, so the whole idea is, what can I do mathematically that will allow me to compensate for this uncertainty? And the compensation that we're going to do is going to be through significant figures. Okay, so a significant figure, significant figures, okay, or significant digits, you may hear it be called. Okay, these are sets of rules that allow us to use numbers to compensate for the uncertainty. So we're always going to be using in our calculations with SigFigs the least certain number. Okay, but before we can identify the least certain number, we have to identify, in which, by the way, the least certain number tends to be the one that has the fewest SigFigs. Okay, we got to have the rules. Okay, the first rule is going to be any non-zero integer. So pretty much any number that's 1 through 9, a non-zero integer, is significant. Okay, and I'm not talking about the numbers 1 through 9, meaning if number 10 is not significant because it's not 1 through 9. And no, I'm not talking about the number 10 as a whole. What I would be looking at is this digit and that digit. Is this digit significant? Is that digit significant? Okay, I'm not talking about the number as a whole. I'm talking about each individual number within the larger number. So if I had 105.263, right, I'm looking at this one, I'm looking at this one, and this one. Okay, now many of you are probably going, well, is there ever going to be a point in which a number would not be significant for a measurement? And the answer is yes. And that has to do with the zeros. Okay, so first of all, number 1, okay, any non-zero integer, numbers 1 through 9, are considered to be significant. Okay, number 2 is talking about, and 2 through 4 actually, talking about zeros, right? There are 3 types of zeros. The first type is what we call a captive zero. And those are the zeros that are in between 2 non-zero integers. So an example of that would be 1.05, or 202, or 5020, or 5021. Okay? Because this zero is between 2 non-zero integers, it's significant. Because this zero right here is between 2 non-zero integers, it is also significant. Here I have 2 captive zeros, right? Those 2 captive zeros are because they have one non-zero integer here and one non-zero integer there. Okay? So that is a captive zero. Captive zeros are always significant, always. Okay? Third rule, we have leading zeros. Leading zeros are those placeholder numbers or placeholder zeros that come before the non-zero integers in a number less than 1, meaning 0.000421, or 0.05, or 0.00000061. Okay? All of these zeros that come before the non-zero integers we call leading zeros, and they are never significant, ever. Okay? Just to drive it home. Okay? Those are never significant. All right? So in this case, if I was looking at this first number right here, there's 3 SigFigs there. If I was looking at this number right here, there's 1 SigFig. If I'm looking at this number right here, there's only 2, because those leading zeros are never significant. Okay? So, last type are trailing zeros. Now, trailing zeros are a little different because there's a little subset rule right here, right? We knew that captive zeros, always. Leading zeros, never. Trailing zeros, maybe, right? Isn't that nice? But it's pretty simple. The identifier as to whether or not a trailing zero is significant is something that is fairly obvious to see, and you'll understand when we get there. But first, we should probably identify what a trailing zero is. Now, hopefully by now we can guess if a captive zero is between 2 non-zero integers and a leading zero comes before non-zero integers, then trailing zeros must come after non-zero integers. For example, we have 100, or we have 2500, or we have 6,402. That's not captive. That's captive. 450. Okay. Anyways, those are all captive zeros, as is any number that comes after. Okay, like say the decimal place. That right there is also a trailing zero. Now, here's the kicker. Okay, even though I have the same number of zeros in every single one of these numbers, all three of these cases do not have the same number of significant figures. Okay. Now let's go and look at the top one, or the very first one. Okay, this one, these are these are zeros right here. This one and this one. But they are not significant. And the reason why they're not significant is because the all-powerful indicator is whether or not a trailing zero is significant is if there is a decimal present in the number. 100, like that, does not have a decimal. Therefore, those trailing zeros are not significant. 2500, again, these are not significant. Why? Because there's no decimal. So how many sig figs do I have here? I have one there. How many do I have here? I have two here. Okay? And then in the bottom one, I do have a decimal in that number right there. Right? And because of that, any trailing number or any trailing zero is a significant figure if there is a decimal in the number. Okay? So in this case, I have 6,450.0. Okay? Because of that, I have 1, 2, 3, 4, 5 significant figures. Okay? So, that's how we identify which ones are significant. Now we look at things of the operational scale, meaning if I have to do some math, right? Well, there's two sets of rules. Okay, there's the multiplication division set of rules, right? And then there's the addition subtraction set of rules. And we'll do the multiplication division first because honestly, about 98% of the time, you're going to be doing multiplication and division in here. You're not going to do that much addition and subtraction. Okay, so for example, let's say I had 510 times 405. Okay? Obviously, I'm going to end up with a big number right here. Okay? Because I'm taking hundreds and multiplying by another hundred, so I'm going to get some big digits here. Now, when it comes to multiplying numbers in this class, you're going to need to look at the number of sig figs in the operation. So if I was to identify the number of sig figs in 510, hopefully you would recognize that there are two sig figs. Why are there two? It's because that zero, that trailing zero, is not significant because there is no decimal in that number. Okay, 405, there are three significant figures. Why? Because that zero is captive. Okay, if that's obviously remember, if these zeros were anything other than zero, they would be significant because that's the first rule. All non-zero integers are significant. Okay, so looking at this, let's go ahead and multiply that. I end up with a whopper of a number. Let's go with 206,550. Okay, very big number. Now, if I was to count the number of sig figs here, hopefully you would give me 5, right? Because that trailing zero is not significant because there's no decimal in the number, but that captive zero is. And remember, they always are. So looking at that, I have more significant figures, meaning there is a greater deal of certainty in my answer than there is in the part that came before, my two numbers here, right? I can't have a more certain answer than what I started with. And in fact, there is one of these two numbers is going to limit the number of significant figures my product has. Okay, and that this was a division, it would be the same rule, right? Bottom line, this guy right here has 2 sig figs. This guy right here has 3. 2 is smaller than 3, which means this number right here needs to be changed to only have 2 sig figs. And it's really simple. All you're going to do is you're going to look at that first number, which is my first digit, and I'm going to drop that down to 2. Okay? The second one is my 0, and then right then and there, everything else will become a 0. But make sure not to put your decimal in there, because if you do, all those zeros become significant, and then we end up with actually 6 significant figures. Now, is this technically correct? No, not yet, because 1, I only have 1 sig fig, okay? Which, that's okay. Sometimes you're going to end up with having fewer sig figs than you started with, okay? but you only are allowed to do that if the rounding permits it. Okay. So, for example, if this was, instead of 206,550, if it was 204,550, this would be your answer. You're not thinking, like, well, how's that possible? Okay, it's because I need to look at that second digit. So I need to look at this guy right here. Right, that's my second sig fig. Then I need to look at the third digit because that third digit is going to tell me whether or not I need to round. Okay, 6 is 5 or greater, which means the 0 right here is actually not going to be a 0. It's going to be a 1. Okay? So the answer, and if you notice, I have 2 sig figs here, right? 21 or 210,000. There's only 2 sig figs there, and that's my answer. And the reason why I have to have that be my answer and not 206,550 is because I can't have an answer being more certain than this number. Okay? So that is the rules for multiplication and division. Okay? With addition and subtraction, it's a little different because I'm not necessarily looking at significant figures. I'm looking at the certainty of my measurement. Okay? So let's go ahead and do an addition problem. Let's go ahead and use similar values. Let's go, or not different ones. 46.3 plus 88.51. Okay? So, in that, I'm going to go ahead and sum it up. And I end up with, in this case, can't see because of my hand. Let's see, 134.81. Okay, so that's my sum. Again, if this was a subtraction problem, that would be the difference. I'm still going to apply the same rules. Okay, there's 2 different sets of rules here. There's the multiplication and division, and then there's addition and subtraction. So, looking at this, I'm looking not so much at the number of sig figs, but I'm looking at the numbers to the right of the decimal. In this case right here, if I was to look at this guy, I'm going, wow, I made that measurement. Because remember, these are all coming from measurements. They're not just whoop-de-doo numbers I made off the top of my head. Well, this video is. But when you see them in a lab or you see them in class, these numbers have meaning because there's something behind them. There's units to go along with them. They're not just random numbers. You're going to learn in chemistry that a number is going to mean nothing without units. Okay, so I'm looking here, that's 46.3. That means that I was able to measure to the ones place, and then I had to estimate the tenths place. Okay? Here, because it's 88.51, that means I was able to measure to the tenths place, and I had to estimate the hundredths place. So let me put that arrow on top just to make it even. Right? So, if I was to look which one of these numbers is least certain or less certain, okay, that would be this guy. Now, looking at this, I have only one number to the right of the decimal here. That means this answer can only have one number to the right of the decimal. So my real answer here, or my appropriate answer here, would be 134.8. Again, always look at this other digit because that, if that was a 6, right, or an 8, if it was 134.88, then my answer would be 134.9 because this digit right here could cause this one to round up. Okay, so you got to pay attention to that. All right, but that's the gist of what uncertainty is, the rules for identifying sig figs, and lastly, how to use these sig figs in math problems. Okay, multiplication, division, addition, subtraction, 2 sets of rules. Don't confuse them. Okay.